In the world of aerospace engineering, few achievements have captured global attention quite like China's most recent breakthrough in hypersonic propulsion. In May 2025, Chinese scientists accomplished what was once the stuff of science fiction, successfully testing a revolutionary engine capable of driving an aircraft to Mach 16, 16 times the speed of sound. This milestone marks not only a leap forward for China's technological prowess, but also signals a dramatic shift in the future of both military and civilian aviation. To grasp the magnitude of this achievement, it's important to understand what Mach 16 means. At that speed, an aircraft could theoretically travel over 12,000 miles per hour, or nearly 20,000 kilometers per hour. For reference, this is about 10 times faster than today's fastest commercial jets, and more than twice as fast as the Concorde, the legendary supersonic passenger airliner. Such speeds could shrink intercontinental travel times from hours to mere minutes, transforming the way we connect across the globe. At the heart of China's breakthrough lies a cutting-edge propulsion system known as the Oblique Detonation Engine, or ODE. The concept of the ODE was first proposed by researchers at the University of Michigan back in 1958. For decades, it existed only as a theoretical idea, a vision of an engine that could harness the raw, explosive power of detonation, rather than the slower, less efficient process of traditional combustion. Unlike conventional jet engines, which rely on turbines and compressors with many moving parts, the ODE is designed to operate without any moving components, instead using carefully engineered shockwaves to ignite fuel instantaneously. The Chinese team's most recent tests pushed this concept further than ever before. Utilizing RP3 aviation kerosene, a widely available jet fuel, engineers managed to sustain a stable detonation wave for more than 2 seconds, while simulating flight at Mach 8 and an altitude of 30 kilometers above the Earth's surface. While 2 seconds may seem brief, in the realm of hypersonic propulsion, it represents a major technical feat, a demonstration that the engine can not only initiate, but also maintain, the extreme conditions necessary for hypersonic flight. What makes the oblique detonation engine so revolutionary is its ability to couple shock waves and combustion in a single, continuous process. As air rushes into the engine at hypersonic speeds, it is compressed by angled shock waves, raising its temperature and pressure to the point where fuel injected into the stream detonates almost instantaneously. This detonation releases a massive amount of energy in a fraction of a second, propelling the aircraft forward with unprecedented efficiency. Because the ODE has no moving parts, it promises greater reliability, reduced maintenance, and lighter weight compared to traditional engines. But the Chinese breakthrough goes even further. In December 2023, researchers unveiled an air-breathing engine design that integrates both rotational and straight-line detonation mechanisms, covering a wide range of speeds. This hybrid approach allows the engine to operate efficiently from lower hypersonic speeds, around Mach 6, all the way up to Mach 16. Such flexibility is a first in the world of propulsion technology, enabling aircraft to accelerate smoothly as they climb through different layers of the atmosphere. The implications of this achievement stretch far beyond the laboratory. For military applications, hypersonic aircraft powered by ODEs could deliver rapid, unpredictable strikes anywhere on the planet, making them exceptionally difficult to detect or intercept. Missiles and reconnaissance platforms equipped with these engines would have the ability to outpace virtually any existing defense system, fundamentally altering the strategic balance between nations. In the civilian sector, the prospect of hypersonic passenger jets is no longer just a distant dream. With engines capable of sustaining flight at Mach 16, a journey from New York to London could, in theory, take less than half an hour. While significant engineering and regulatory challenges remain, the successful demonstration of a kerosene-fueled ODE opens the door to the possibility of practical, affordable hypersonic travel within our lifetimes. Achieving this level of performance, however, is not without daunting challenges. Hypersonic flight exposes both engines and airframes to extreme thermal and mechanical stresses. At speeds exceeding Mach 10, The friction between the aircraft's skin and the atmosphere generates temperatures hotter than molten lava, threatening to melt even the most advanced materials. Chinese scientists have had to pioneer new heat-resistant alloys and composite structures capable of withstanding these infernal conditions for sustained periods. Moreover, the detonation process itself is inherently unstable and difficult to control. Creating a stable detonation wave that can be sustained long enough to generate useful thrust without destroying the engine or the vehicle requires exquisite engineering and real-time control systems. The successful 2-second demonstration may be just a glimpse of what's possible, but it paves the way for longer, more ambitious tests in the future. The global response to China's advances has been a mix of awe and apprehension. While the ODE was first theorized in the United States, China's rapid progress in turning theory into practice has raised questions about the pace of Western innovation. The race for hypersonic supremacy is no longer just about speed. It's about materials science, computational modeling, manufacturing precision, and the ability to integrate complex systems into operational vehicles. Beyond the technical marvel, the potential impact of hypersonic propulsion on society is immense. In addition to revolutionizing travel and national defense, these engines could enable new forms of space access, making it possible to reach orbit more efficiently by skimming through the upper atmosphere before igniting rocket boosters. Scientific missions, emergency response, and global logistics could all benefit from the ability to traverse vast distances at breathtaking speeds. Yet, as with any transformative technology, the rise of hypersonic propulsion brings new responsibilities and risks. The same capabilities that promise to unite the world could also destabilize it, as nations scramble to adapt to a landscape where the old certainties of distance and warning time no longer apply. As China continues to lead the way in hypersonic research, international dialogue, cooperation, and the development of new norms will be essential to ensuring that these advances serve the common good. In the end, China's successful demonstration of a jet-fueled engine capable of reaching Mach 16 is a testament to human ingenuity and the relentless pursuit of progress. What was once an audacious idea on paper is now a tangible reality, opening avenues to a future where the boundaries of time and distance are redefined. As the world watches this new era unfold, one thing is certain: the age of hypersonic flight has truly begun, and its journey is only just taking off.